Okay, so welcome to this lecture, and today we're going to talk about Baire spaces, and we shall prove the Baire Category Theorem, okay? And then we're going to discuss the convergence of functions again, okay? So we will define Baire spaces, and then we're going to show that complete metric spaces and compact Hausdorff spaces, which are the two most important spaces we studied, they are Baire spaces, okay? So before that, we need a definition. Given a space and A is contained in X, we say that interior of A, we have to find interior A, right, which is the union of all open sets and X that are contained in A. And we said A has an empty interior if the interior of A and X is equal to the empty set. And then we also have that if A has empty interior, then the complement is dense in X. And here are the verifications, okay? And we have some examples. So Q is definitely empty interior, right? Because the irrationals are dense in R, right? The irrationals are dense in R. And the interior of this is not empty, right? Because 0, 1, right, is contained in this. And Q times R is has empty interior, right? Because the complement, which is the irrationals, times R, right? Just some examples of empty interior sets. So we say that we can finally define a space is a Baire space if for any countable collection of closed sets such that each has empty interior, then their union also has empty interior, okay? So this is the definition of X being a Baire space. So an example again, the rational is not a Baire space, right? Because one point set and Q, they're closed, right? And they have empty interior. And Q is the countable union of those one point sets. So Q is not a Baire space. Some lemma. So we have, this is the closed set definition. And then we also have a open set definition of a Baire space. So we said F is a Baire space if and only if for any countable collection of open sets such that each is dense in X, then their intersection is also dense in X. Okay, and this lemma is really just by this, right? It's just by this definition apply with this. Okay, because if they're close, so for example, they have empty interior, then the complement, right? If A is closed, if A closed, right, closed, dense, if and only if X minus A open, right, open and dense in X, right? So it is just by the definition and our remark above. And now we're going to prove the Baire Category Theorem. It states that complete metric spaces and compact Hausdorff spaces are Baire spaces. So let's just start with a given countable, closed, empty interior collection, right? And we show that this also has empty interior. So we want to show that. To show this, we want to show for any non-empty open set in X, there exists a point such that it is not in this, right? Because if we want to show that this empty interior, right, then for any non-empty open set, right, we have U not a subset of the ANs, right? If they are not a subset of this, we must have there exists a point in U naught such that it is not in this, right? So we need to focus on this. And to focus on this, we're going to construct a sequence, okay? So first we consider A1, then because U naught is not a subset of A1, right? Because each of them have empty interior, right? So A1 has empty interior, so U naught is not a subset of A1, So we can pick a y. We can pick a y, and is not an A1, and as x is regular, right? X is regular because metric spaces are normal, compact Hausdorff spaces are normal, and normal spaces are regular. So as x is regular, no matter what, we can pick a neighborhood of y such that this is true, okay? If x is a metric space, then we can make U1 small enough such that it is contained in the one ball centered at x. So in general, suppose UN minus 1 is chosen because AN has empty interior, so this is not a subset of AN. So pick a Y and UN minus 1, and it's not an AN. Okay? And then again, we pick a neighborhood such that this is true. If X is metric, we can again make UN small enough such that it is contained in the 1 over n ball centered at X. Okay? So from here, we have two claims. So given the sequence of UN we constructed, we have this is true. Well, if X is compact, right? If X is compact, notice we have this is true, right? We have this relation, right? Because this is how we define, right? So we first have this relation. It has finite intersection property because each of them, right? Each of them are non-empty, right? Each of them are non-empty. So we have this is true because X is compact. If X is complete, because we have a decreasing set in each UN, their diameter is also decreasing, right? So if we pick a sequence Xn and Un, this is automatically a Cauchy sequence. So it converges to some X. Well, if it converges to some X, then this X must be in the closure of Un for any n, right? Because for each X fixed, for each K fixed, this subsequence converges to X2, right? So we're done. So we have proven the claim 2 that this is true, right? So suppose X is in it, then X, first of all, X is in U1 bar, it is in U naught. Right? So for X is U naught, and X is not an AN for any n, right? Because we have this is true, right? So we're done. We have a point X that is in U naught and is not an AN. Now, so we have that complete metric spaces and compact Hausdorff spaces are Baire spaces. So back to the study of convergence of functions, right? So given a sequence of continuous functions such that it converges to some function pointwise on from 0 to 1, and we know that this f is not always continuous, right? F is continuous only it is uniformly convergent, right? But we only have pointwise, so f is not always continuous. But how discontinuous could f be, right? So this is our question here. We know that is discontinuous, but how bad it could be behaved, right? So first we need a lemma, is that open subspace of a Baire space is a Baire space. Well, the proof is not long. Okay, so given the collection as usual, right, it is in Y. So if this is the closure of A and X, then because they're closed in Y, so this is true, right? So first we have the claim that AN has empty interior in X. To prove this, if U is open in X and non-empty open set that is contained in this, okay? Suppose for a contradiction. Then, first of all, from here, we have that U and AN intersect, right? If U and AN intersect, which means that U and Y are intersect, they're non-empty. From here, that this is a non-empty set open in Y, right? This is a non-empty set open in Y. And U intersect Y from here, right? U is subset of A and bar, so it both intersect Y. So U intersect Y is a subset, right, of AN. So we have a non-empty open set in Y that is contained in AN. Contradict the fact that they are like empty interior in Y, right? So we have a contradiction that, so we have this claim. So if they contain some non-empty open set in Y, then this also contains like W, right? And W is open in X because Y is open in X, right? And this contains a non-empty open set in X, which by claim 1 is a contradiction, right? Because they have empty interior and X is a Baire space, so they must have empty interior too. But we have shown that it contains a non-empty open set in X, so we have a contradiction, right? So this contains no open sets in Y, okay? So we're done. And so we have the final theorem for this lecture. That, so if X is a space and Y is a metric space, then we have a sequence of continuous functions such that it converges to a function pointwise. Now, if X is a Baire space, then this set C, okay, C is the set of points where F is continuous at it, okay? Then, if X is a Baire space, then C is dense in X. That is, the closure of C is equal to X, which means that if X is a Baire space, it is continuous almost everywhere, right? Point of continuity, it is actually dense in X, okay? Topologically dense in X. And to prove this, we first need a claim. We first need a definition of A and epsilons. So for n and epsilon fixed, we define A and epsilon of the point X, for which for any nm greater than n, this is less than or equal to epsilon, okay, less than or equal to epsilon. So the first claim is that it is closed in X. Okay, to prove that it is closed in X, we're gonna consider set B and N. Okay? Then, first we have a subclaim that the metric function is continuous for any metric space. Okay? And the proof is here. I'll give you time to screenshot it. So as Fn and Fm are continuous, then the mapping that sends X to Fnx and Fmx are also continuous. And with the fact that D is continuous, then the mapping that sends X to the distance between them are continuous. And we denote this mapping as a letter, okay? Then B and epsilon by definition is equal to this, which is again closed, okay? So A and epsilon is a intersections of closed sets, which is closed. Okay, so we have A and epsilon are closed. Now for epsilon fixed, we consider the increasing chain, and then we have first a pointwise convergence, where so each of them is Cauchy, which means that Xn is an A and epsilon for sub n, which means that this increasing chain actually expanded to the entire space X, okay? And then now we're gonna let U epsilon denote the union of those interior of those open sets, which is an open set. Now we have a second claim that they are dense in X, okay? So to show that they are dense in X, we want to show that if it's non-empty open set, right, then it must intersect with U epsilon, right, which is it must intersect with this force on n. And to do this, first of all, first because AN is closed, right? AN is closed in X. So this is closed in V, right? And by lemma, because V is open, right? So V is a Baire space. So this is they're closed in V, and V is a Baire space. So if each of them have empty interior, then the union of them have empty interior in V, right? Which means that this set is equal to this set, okay? Then this is equal to, they expanded at X, right? So V has empty interior in V, which is clearly ridiculous, right? So which means that this is false, right? So there exists an N such that V intersect A and epsilon contains some non-empty open set in V, right? It's not empty interior. And W is open in V, V is open in X, so W is open in X. Hence, we have a W non-empty open in X, and a W open in X, and W is contained in A and epsilon. So W is contained in interior A and epsilon. So we're done. Okay. Right. This is what we want to show. Right. This is what we want to show. For any non-open, so we have this non-empty for set n, and we exactly have this non-empty for set n. And we have a third claim, is that C contains our definition of U1, of U epsilon, of those, it contains it as a subset. Well, to do this, recall the definition of U epsilons, right? We define the U epsilons as this. This is an open set, okay? So suppose that we want to show this, right? So suppose X naught is in all of them, right? Then for any epsilon, first we pick 1 over K as less than epsilon over 3, and X is in this U1 over K. So if it's here, then it must be in some interior of AN, right? For some N, AN 1 over K. Now for this N, Fn is continuous. So we pick a neighborhood of X naught such that W is contained in this, and from here, right? First of all, X is an interior, so we can pick a neighborhood W such that it is contained in this. And then we can make it even smaller such that it satisfies the continuity of Fn, okay, at X naught, right? So, and yes, first of all we have this, right? And this condition also gives that for any X and W and for N is greater than N, we have this is true, right? By the definition of this, less than or equal to 1 over K. And from here, if we just let N goes to infinity, this goes to X, f of X, right? Because we have pointwise convergence. And yes, this is true. Now, also, why is it not moving? Oh my god, why is it not moving? Okay, also, for X naught and W, right, we have this is true, right? If we just replace X by X naught. Okay, why is this not moving? Right? Give me 1 second. Okay, so for X and W, we have this is true. So X and C. Okay, so now since my screen, okay, it starts working again. It just starts working again, okay. So we just by the triangle inequality, right? Okay, we have those three. Okay, now we have this, this, and this, right? So we have fx, so fx and fnx, fnx and fnx naught, fnx naught and f of x naught. So we fx all the way to f of x naught is less than epsilon for x and w, right? So we have for any epsilon greater than 0, we have the neighborhood w right? With a neighborhood W of x naught such that for any x index, x and w, we have this. So x naught is the point for which f is continuous, right? So we have this. Okay, so now finally, each of them are open, dense in X. So this intersection is also dense in X because X is a Baire space. Now, we have this is this, right? Because we have this. So C is dense in X, as desired. Okay, so this is a very beautiful result. Shows that under Baire spaces, the limit function is continuous at the points for which is dense in X, almost everywhere. Okay, so it won't be that bad. Okay, and this is everything for this lecture, and I'll see you guys next time.